This is Spring 2010, quiz number 3, problem number 2. So this is titled Software Detective. This is the kind of problem that we also refer to as a stack detective problem. And these problems are going to test your knowledge of how procedure linkage and procedures themselves are going to interact with the stack. So how we use this special data structure to keep track of arguments across various procedure calls. We start off getting some chunk of C code here, and then we see how it turns into assembly, right? And then we also can see over here what the stack looks like after that code has run for a while. So we're given the listing C program, its translation. So the first thing that they want us to do, part A, is they say in the space below, fill in the binary value for the load instruction at the location tagged YY. So by binary value, I'm just going to move the canvas a little bit. By binary value, what we mean is we mean the way that the bits on this instruction here, tagged YY, are going to get stored. So you probably remember that we have these sheets. So on these sheets we see that BP, which is one of the registers that this load needs to save in the binary data, is number 27. And we also see that the last 16 bits are going to be a literal in 2's complement, which is the integer that's in the middle of the load instruction here. So, and also we see the opcode is 011000. So the opcode is 011000. And then we said that register C here is register 1 in the instruction. So that's 00001. And then register A is BP, which is number 27. So 27 is the same thing as 31 minus 4. And 31 is all ones, so this is 31 minus 4, right? Take away the one that was in the fourth place. Okay, so now I just have to have the literal here, which is supposed to be minus 12. So I have to figure out how to make minus 12. So first, I can start off, I know how to make 12. So this is a 0 in the 1's place, a 0 in the 2's place. We need 4 plus 8 should give us 12. And everything else can be 0. Dot, dot. Now we need to flip the bits, so 1 dot 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 1 1. These are all ones, right? Flip the bits, and now plus 1. So if we add 1 here, it'll carry the 1. So 1 plus 1, 0, carry the 1, and then we have 1, and then everything else is just the same. 1. So this is how we're going to do negative 12. 0, 0, 1, 0, and then the rest ones. Alright, there we go. Now we have our answer for part A. In part B we're asked, suppose the move instruction at the location tagged MM were eliminated from the above program. Would it continue to run correctly? Well, what this instruction's doing is when you have your stack before this program starts to run, right? We'll just draw what we think the stack frame's going to look like. So we have the arguments in reverse order on the stack, right? So X is the first one it wants, and then Y. Okay. And then we have the old LP pushed. That's thing number 1 here. And then number 2 is we have the old callers BP pushed, and then step number 3, we move the current stack pointer value to be the base pointer. So this is the new base pointer. And then after we do that, you know, we do 2 other things. We have old R1 from the caller and old R2. But we're going to do load BP minus 16 into R0. So BP is right here, BP minus 4, 8, 12, 16. The thing at BP minus 16 is going to go into R0. And then here, the thing at BP minus 12 is going to go into R1. So because of that, because we used this value of the BP, which happened because we assigned it at the instruction tagged MM, then we cannot get rid of that instruction because later instructions depend on that value in order to load the proper variables to this function. So now we'd like to go over part C. We want to find the missing expression designated by all the question marks in the C program above. So what we're going to have to do is, because we're missing the information in the C code, we're going to have to walk through what the assembly here is doing. We know that this program here is going to be expecting on the stack, like we said before, arguments in reverse order, so y and then x all the time. So we have two cursive calls here. So let's figure out what the arguments to those are. Now we've just filled in the rest of the stack frame from before. Given that this is the BP, this is BP minus 16 because it's 4 lines. And then this one is BP minus 12. So that means that y is going to go into R0 and R1 so far is going to contain x. So next thing that we do, we subtract R1, 1 from R1, put it in R2. So R2 is going to contain x minus 1, which if you look right here is a. And now we're going to add 0 to R1, R0 to R1, so y plus x, and put the answer in R1. So this is going to get clobbered. It's going to be b, which is x plus y. And then we're going to push them. So notice, because we're pushing in reverse order, and we're going to call f, right? So that's why we know that these are the arguments to that function. We're pushing R1, so that means b is going to be in the y place here. So this call is going to be f of, we said that because this one was pushed first, right, then it must be on the top here. B goes here, and a this is, sorry, the new y. The new y and the new x for the recursive calls, which based on what was in these registers are going to be equal to a and b. So then this, after all that, then we're going to have the return of this function left in R0. So then we're going to load BP minus 16 into R1 again. So we said that was y. And then we're going to add the thing in R0 plus y. We're going to put that in R0. So now this gets clobbered because we're replacing it here. So then this is y plus f of a, b. And then that is going to be our new second argument, first argument, right? So this is another function call here, right? This is going to be f of, and the thing that was still in R2 is a, so a, and the thing in R0, which is this, so. Okay, so now we have our answer. This is the question mark part here. So y plus f of a